Sonia Velasco, who's going to talk to us about the quasi-potential for the SSEP in weak contact with reservoirs. So Sonia, you have the floor.
Thanks. So you can see my screen, you can hear me, everything's fine?
Yeah.
Okay.
Everything's all right.
Okay. So first of all, let me thank the organizers for the invitation. It's a real honor for me to be able to give this online seminar. And I apologize for those who have already seen this talk. It's pretty much the same talk as the one I gave less than a week ago. So sorry. Okay, so this is a joint work with Claudio Landim from the IMPA and the LMRS. And the model we looked at is the widely known symmetric simple exclusion process, okay, which many of you know very well, but just to fix the notation, let me remind you how it works. So you have particles evolving on sites numbered from 1 to n-1. They perform symmetric random walks at rate 1 with the constraint that a particle does not jump to a neighboring site. And to the system, you attach some reservoir of particles with certain rates. So for example, the left-hand side reservoir has rate alpha. That means that it injects particles at rate alpha and removes them at rate 1 minus alpha. So configurations in this setting will be denoted eta. And from what I understand, this is a very elementary toy model, which is extremely rich when it comes to understanding diffusive mechanisms. And also it's a good starting point when trying to build some non-equilibrium stationary states. So in the physics world, what we mean by a stationary state is basically a state of a system that is independent of time. And mathematically speaking, this will be basically an invariant measure. So here, because of the reservoirs, we have an irreducible system. The state space is finite, so you have one unique invariant measure. And when alpha is beta, so you have thermostats at same temperature, this measure is reversible, so the system is at equilibrium. And it's actually explicit. It's a Bernoulli product measure with parameter that of the reservoirs. But when alpha is not beta, that's when you've managed to build a non-equilibrium stationary state, in the sense that you have an invariant measure, which is much more complex. So first of all, it's not irreversible, meaning that the detail balance condition is not satisfied. And you have a flux of particles appearing. And okay, in a general setting where you have a system driven out of equilibrium, it's very difficult to make sense of this object. Here it turns out you can write it down explicitly. But okay, in general, how can one try to make sense of this invariant measure? So what you can do is look at its scaling limits. And to do that, you want to embed all your objects in the same common state space. So you look at the empirical measure associated to a configuration. And the first natural question to ask is there a law of large numbers for your empirical measure? In which case, you are able to say that pi n converges to the measure rho x dx, where rho is a profile defined on your continuous counter space of counterpart of the discretized space. And the convergence happens under your steady state. Okay, and the second natural question to ask is, do you have a large deviations principle for the steady state, in the sense that you can quantify the probability of observing another profile rho hat, which is not that of your law of large numbers, and you'd like to write it as an exponential of minus n times a certain functional. So this will be written in a more rigorous way later on. And you want that this rate functional is 0 when rho is your law of large numbers. Right. Okay, so these questions have been answered thanks to the matrix ansatz method devised by Derrida. And actually that method provides an explicit expression of this steady state. So it answers many more questions than the law of large numbers and the large deviations. You can also look at the correlation structures, etc. So here's the picture. You have your interacting particle system at the microscopic level. You want to understand its scaling limits. under the steady state, and you can use the matrix ansatz in the particular case of the symmetric exclusion process with reservoirs. Okay, I think you can generalize it to similar models, but it remains, let's say, model dependent. And I mean, recently I discovered that there are other methods to perform, to get some information on these steady states. For example, you can use duality. Okay. So what you do is you have an interacting particle system at the microscopic level, and you say that this interacting particle system is dual to another interacting particle system for which it's maybe easier to write some algebraic relations from which you can extract some information at the macroscopic limit. Okay, but to me, these methods are very, let's say, magical. Maybe it's because I don't have a very, I'm not very knowledgeable about algebra and all of that. But let's say these methods are quite model dependent and rely on nice algebraic relations. But okay, then you might want to say, as a physicist, you might want to say that there is a principle of life that is that when you wait for a long enough time, you expect that if you start your system in a certain way, that is not necessarily at the steady level, and you have a time-dependent behavior. If you wait for long enough, the system should relax to the steady state, okay? So another route you can take is the following. You start your system at the microscopic level at a certain measure mu n, which is not the steady state. You perform a scaling limit, so then you get a law of large number that depends on t, which is the called a hydrodynamic limit. You get a dynamic large deviations principle that also depends on t, and then you take t to infinity. Okay, in a certain way. I'll make this precise later on. So this second route, referred to as, which uses what is called macroscopic fluctuation theory, has been made. Okay, it's not always rigorous, right? Because sometimes it's very difficult to write. For example, for non-gradient systems, it's very difficult to prove rigorously a hydrodynamic limit. And for systems where you have maybe infinitely many particles which can live on each site, well, maybe it's very difficult to make rigorous this dynamic large deviations principle. Okay, so this second route can maybe give you some intuition on what you should have at this level, but sometimes it's not rigorous. However, in the case of the SEP with reservoirs, it's rigorous. It's proved mathematically speaking. But then for other models, I'm not so sure. Okay, so let me tell you how this works for the SEP with reservoirs, where this is formal. So you have your interacting particle system, and now you'd like to see some time-dependent behavior. So what you need to do for that is to renormalize the rates. Here we have a diffusive process. We take a diffusive scale, and it's been proved in 1990 by Eink, Lebovich, and Spern that this P mu n, so the measure induced by the dynamics when starting from any initial measure, concentrates on the trajectory rho tx dx, where rho is the solution of the heat equation with Dirichlet boundary conditions. Okay, then in 2003, so these MFT people that I didn't cite in the scheme, but here they are, so Bertini, Desolé, Gabrieli, Ioannalassino, and Landim, proved dynamic large deviations principle around that hydrodynamic limit. So I said I would give a rigorous statement of a large deviations principle. So here it goes. So you fix an initial profile rho 0 with certain properties, and you suppose that initially your configurations are associated to rho 0, right? So you need to fix your initial condition. Okay, so you have these measures. They live on a space of trajectories which are time-dependent with values measures. These measures satisfy the following large deviations principle. So for any open set O in that space of trajectories and closed set F in that same space of trajectories, the following lower bounds and upper bounds hold. So you take 1 over n of the log of the probability, which is what you want because you wanted to write the probability of something as an exponential of something, okay? And these bounds, lower bounds and this lower and upper bound match. So you're happy because this is what tells you that you managed to get a large deviations principle. And what's important here is that, so this large deviations functional depends on time and on a given initial condition, right? So now, how do we take, how does this relaxation picture work? So taking t to infinity. Well, it turns out that from the hydrodynamic limit, you can take t to infinity and recover your law of large numbers at the static level for your invariant measures. Right, so what you say is that you use that any solution to the heat equation with Dirichlet conditions will converge to rho bar, where rho bar interpolates alpha and beta. And actually, you can use this fact, which is purely analytical, to prove that this measure is associated to rho bar. Okay. Then how do you take t to infinity at the level of the dynamic large deviations functional? So that's maybe a little bit more subtle to make sense of. So you define the so-called quasi-potential, which is the following object. So the quasi-potential is a functional defined on functions which only depend on space, right? Because you're trying to build a large deviations functional at the static level, so on functions which only depend on space. And here is its definition. So you take the infimum over all space-time dependent trajectories which connect rho bar and rho. So at time 0, you're equal to rho bar. At time t, you're equal to rho. You take your dynamic large deviations functional evaluated at that trajectory, which took you from rho bar to rho. So your large deviations functional with the initial condition rho bar, and you take the infimum over all times t of this cost, right? So basically the quasi-potential is telling you the price you have to pay using your dynamic large deviations functional to go from rho bar to rho. And so in that same paper in 2003, these authors proved that the steady state satisfies the large deviations principle with speed n and rate function, the quasi-potential v. And thank God they found the same functional v that was found independently by Derrida-Leibovitz and Speer for the SSEP with reservoirs through the matrix ansatz methods. So, I mean, these people, they worked pretty much during the same years, and following these two methods, they found the same rate functional at the static level. And just note that for alpha equal to beta, this is nothing else but the entropy of rho with respect to alpha. Okay, so if you have alpha which is not beta, you would have some non-local term appear. Okay, so now after this introduction, let me tell you which model we looked at and for which we tried to adapt these same ideas from macroscopic fluctuation theory. So we looked at the same model, except that we have very slow reservoirs, right? So you have particles which are n to the -2 slower than particles evolving in the bulk. Okay, your particles in the bulk evolve with speed n square, and your particles at the reservoirs with p to the order 1. You denote nu slow n the steady state, and we would like to recover the static large deviations for nu slow n using these ideas. Okay, so in 2017, Baldasso, Meneses, Neumann, and Arsouza proved that the hydrodynamic limit for this model is the heat equation with Neumann boundary conditions, okay, which is quite natural because your particles are entering so slowly that macroscopically you don't have any flux happening at the boundaries. Okay, and in particular, let me make the following remark, which will be useful in what follows. So for an ET, you have some conservation of mass, right? The mass, what I call the mass of rho, is the integral of rho in space. This is always equal to rho 0 x dx. And you also have that rho tx relaxes to that constant, right? So you get many, many stationary solutions. So you don't really know which one will be the one which corresponds for your law of large numbers, okay? So even at the level of the hydrodynamic limit, it's not so sure how to make sense of this relaxation phenomena. And in that same paper, the authors proved law of large numbers for the steady state, but they did not actually use they didn't use the hydrodynamic limit. They just stayed at the macroscopic level and sort of controlled the correlations and performed some relations which were completely macroscopic, okay? Then in 2021, Franco, Gonçalves, and Neumann proved a large deviations principle for this model, okay? So they proved that you have a large deviations functional that is IT slow with respect to a certain initial condition, okay? And now we have the analogous of this mass conservation remark that I made before, which holds here in the sense that you have this functional, it explodes if there is a T such that the mass of rho is not that of rho 0, right? So even at the level of the large deviations, you're not allowed to change your mass, right? The cost is explosive.
Sorry, Sonia. So this is because you have a diffusive scaling, right?
Yeah, exactly. And in particular, you can't make sense of this object, the quasi-potential, when, gamma is alpha plus beta over 2, your law of large numbers profile. You can't make sense of this quasi-potential if rho does not have total mass equal to gamma. Okay, so let me remind you the picture. We're trying to, so this is this part of the root is already done. So the hydrodynamic limit and the dynamic large deviations for the this with slow reservoir, for the SSEP with slow reservoirs. But now we'd like to do this part of the root, and it's not really sure now. I mean, we're kind of blocked because of this mass problem. Okay. So as Clément just said, because we're looking at a diffusive scaling, there's no hope to see some change of mass, right? So we need to look at another scaling. And what we did is to look at the following scaling. So you accelerate all your rates by n. So alpha n, of speed of order n at the reservoirs and speed of order n cube in the bulk. And there, I mean, okay, as you've multiplied your rates, the steady state doesn't change. You can do whatever you want. And there, we're expecting that at this new time scale, there should be some evolution of the mass. Okay, so now the new observable that we're interested in is the mass of a configuration. Okay, so what I call mass of a configuration is just the sum of the eta x divided by n. And so now we're trying to understand the hydrodynamic limits of the mass and the large deviations for the mass. Okay. So we proved that the hydrodynamic limit for the mass is a certain profile m of t. So now m is just an function that depends on time, okay? Where m satisfies the following ODE, okay? And so actually, I mean, you can just write M of t is gamma plus M0 minus gamma exponential minus 2t. Okay, you can solve this explicitly. So gamma is alpha plus beta over 2. And just a remark, so after putting the paper on the archive, Kenkishi Tsunoda told us that, I mean, he had that same result than us, but we weren't aware of it. So I cited him here. And in order to prove that, you perform a replacement lemma, right? Where you show that basically you have, so you can replace eta at 0 and at n-1 by the mass of the whole configuration. Basically, that's what you have.
Sorry, another quick question, if you'll allow.
Yeah, of course.
So here it's very important that you have multiplied your scale, your time scale by n and not by something else, right?
Yeah, absolutely. That's where tuning the right time scale is important.
Yeah. Okay.
Absolutely. Okay. Also we proved that, right, so as you're accelerating your process, you might ask, okay, you've given us the hydrodynamic limit for the mass. What about the hydrodynamic limit for the empirical measure? Well, as you accelerate your process a lot, it becomes immediately flat, right? So we also proved that if you fix an initial profile row 0, you take mu n associated to row 0, then at any time t, you have the following convergence in probability. So your empirical measure concentrates on the constant function, okay, on a function which only depends on time, mt, where m is, gamma plus m0 minus gamma exponential minus 2t, okay? And from these two results, so the hydrodynamic limit for the mass and that one for the empirical measure, you can recover by taking a large T limit, this measure is associated, the law of large numbers of this is the constant profile alpha plus beta over 2. And so what's nice is that I think that in the paper where they proved it using some microscopic tools, the method was very one-dimensional, because in order to control these correlations, they had to use some kind of random walks. I mean, I can't remember the proof very well, but it was very one-dimensional. And I mean, this new idea using time relaxation allows to get rid of this one-dimensional problem. Okay, and if I remember rightly, actually, Tsunoda also proved in his paper using this hydrodynamic limit for the mass, this same law of large numbers through this relaxation method, although he didn't use that. But anyway, okay, so now, so just to remind you of the picture, so now we've completed this part of the picture, but just for the law of large numbers. And we'd like to do it for the large deviations, right? But remember, the quasi-potential explodes because of this mass problem. Okay. So the first thing to do is to establish a large deviations principle for the mass, right? So we proved that if you fix a certain mass m0, I mean, now in a sense, it's nicer than dynamic large deviations for empirical measures, because objects are less complicated. Now you're looking at trajectories which are only time dependent, not space-time dependent. So you fix an initial mass m0, you consider a sequence of configurations such that your mass initially is associated to m0. And we have that the sequence of probability measures, so p delta eta n, satisfies the following large deviations principles. So for any closed subset of your space of time-dependent trajectories, and for any open subset of that space of trajectories, you have the following upper and lower bounds. Okay. So, oops, sorry. Okay, I don't know what happened. Okay, so you have a large deviations functional, which now takes now is evaluated at functions which are only time dependent and with respect to a constant between 0 and 1. Okay. And so what is this IT of A? So, okay, so you have A with respect to M. This is the supremum over GTA of a certain time test function. So if A of 0 is M0 and plus infinity, M and plus infinity otherwise.
Oh, Sonia, may I ask a question?
Yeah.
So in this theorem, so something that I'm puzzled about is that so if you look at only at the mass of the of your system, this is a very low level observable of your Markov chain. So in principle, it would be difficult to prove a large deviations principle because I mean, maybe I don't know. I mean, one has to figure out that changing, you know, a density to make the profile not constant is not favorable at the level of large deviations, no?
Right. So this is a large deviations principle for the mass, not for the empirical measure.
Yes, but still, I mean, it could be that for some reason, I mean, one says that so it's a little bit more about the proof, no? That it's not obvious to me that proving a large deviations principle for such a low level thing, so only look at the mass of the trajectory, it can be done without passing through proving the large deviation principle for the whole empirical measure and doing like a contraction principle.
How can I answer this? So to you, this is surprising that we managed to prove large deviations for the mass. I mean, okay, yeah. So the mass, right? The mass is not a Markov process.
Yeah.
I mean, the mass is very weird object because it can jump for no reason. You don't have okay, but it turns out that you can still write Dean-King's formula.
Okay.
I don't know if that's a satisfying answer.
No, it's okay. I mean, if you say
because
so, I mean,
you don't need to write your Dean-King's formula. You don't need the mass to be a Markov process because the mass is you're already applying some kind of test function, right?
Mm-hmm.
And I mean that's a blessing. I mean that saves everything, right? You write your exponential martingale. I mean the method to prove this large deviations result is really very standard. You write your exponential martingale for the upper bound, and then you use a perturbation, and for the perturbation for the lower bound, you use some exponential of functions that only depend on time. And then you say that in order to observe a trajectory A, you have to choose H so that H and A are related in a certain fashion. And then you say that you've solved your variational problem. You prove that this, right. But okay, despite the fact that indeed M is, it's true, it's not it's a hidden Markov process, right? Okay. So but it works.
Okay.
But okay, maybe later on I'll comment on something which is maybe related to your question.
Okay, thank you.
So then we prove, for now we're really dealing with the mass. I'll connect to this relaxation thing afterwards. So then we computed the quasi-potential for the mass, so the minimal cost to take your mass from gamma to profile A, okay? And we proved that this quasi-potential for the mass is the static large deviations functional for the mass, okay? And we also got that this quasi-potential, this variational formula can be solved, and it's the entropy of M with respect to gamma. Okay. So now we want to recover the static large deviations for the SEP in weak contact with reservoirs. Okay, and now you're maybe wondering, but we only have information for the mass. So for now, we have information at the level of the law of large numbers. We know that this steady state is associated to alpha plus beta over 2. And we want to, we're missing that part. We want to get that under the steady state, the probability that the empirical measure looks like a certain profile rho, which is not gamma, is exponential minus n times this v slow of rho, which we're trying to catch. Okay, so the idea is the following. You take a profile rho, okay, and you denote by m its mass. Okay, and you want to compute the cost that will take you from gamma to rho. How much does it cost to do that? Gamma and rho. So the idea is that you first accelerate your process by I mean, you accelerate it a lot, right? So in the bulk, you have particles with speed of order n to the 3. And then the idea is that you compute how much it costs to go from gamma to mass m, okay? And you say that to pay that price, it's exactly that quasi-potential V gamma m, right? So you pay the price V gamma m to go from mass gamma to mass m, and then to go from the flat profile, which corresponds to right mass m, to, okay, maybe this is not very well drawn, but never mind, to rho. To go from m to rho, you have to pay another price. So maybe Vm slow rho. And you pay that price by looking at the model in the diffusive scaling, right? Where the mass in the diffusive scaling is not allowed to change. Okay, of order 1. So the heuristics is the following. You have to do V gamma m plus Vm slow of rho to recover the static large deviations functional. Okay, but what is that object? I haven't told you what that is yet. Okay, so who is this Vm slow of rho? So recall that Franco, Gonçalves, and Neumann in 2021, they proved dynamic large deviations principle for the SEP with slow reservoirs, and I told you that this object explodes if rho does not have mass rho 0. Okay, but what about if rho does have mass, the correct one? Well, if you fix a mass m and a profile rho with mass m, you have that you can actually solve this variational problem and show that Vm slow of rho is nothing else but the entropy of rho with respect to m. And actually, you recover this quasi-potential is the same one as if you looked at a SEP with reflecting boundaries, right? So then the idea is that you have this quasi-potential that helps you, that allows you to change mass, this quasi-potential that allows you to go from your mass to your profile rho, and when you sum the two, you recover this total, I mean, your final large deviations functional at the steady state. Okay, and now maybe you're wondering, okay, why am I summing why am I performing the sum to get the quasi-potential that I'm looking for? And here's your answer. So the answer won't be satisfying. It's at the heuristics level. So you want to observe under the steady state your profile rho. Okay. Then you say that this is, as you're working under the environment measure, this is the same thing as writing this under the accelerated dynamics, right? So when you have particles evolving at n to the 3 in the bulk and at n at the boundaries. Okay. Then you say that this, roughly speaking, is so at time t, you're like rho, and a little bit before that, your mass was that of rho. Okay. And then, okay, so then you say that this is, you have intersection of these two events, you split this into a product. So at time t minus t0 over n, your mass looked like that of rho. And then at time t, so then you have, okay, you have a conditional event. So you condition on the fact that at time t minus t0 over n, your mass was that of rho. Okay, so this, you have a product of probabilities. This is where you're going to get your sum of exponential. Why? Because, so here you use the quasi-potential for the mass. Okay, so this is an exponential of minus n times v gamma m. And now here is the part where this is not rigorous. So you have that between t minus t0 over n and t, between these two times, you have a process that is in the diffusive scaling, right? Because you divided all your rates by n. Okay. And you know that in the diffusive scaling, using a the quasi-potential associated to rho when rho has the correct mass, this is exponential of minus m times, okay. So the one with the quasi-potential for the reflecting boundary conditions, right? So this is where you get that it should be the sum. But I mean, you can't really write this that way because in this term, you only have information on the mass at time t minus t0 over n. And I mean, to use your results, your large deviations results, you need to have more information than just information on the mass. So, okay. Okay, it's already 44. Maybe I'll just conclude so that we can discuss afterwards. So to conclude, it turns out that the static large deviations that we obtained heuristically can be obtained rigorously thanks to the matrix ansatz method, okay? And actually the work started from that. We saw a talk by Derrida where he said that using his method, he could prove the static large deviations for the SSEP with slow reservoirs. And we tried to obtain it through this MFT method because we saw that there was a scaling problem. So it would be interesting to make this sum licit because maybe it could become useful for other models where you also have these scaling problems. Okay, so thank you for listening. I'll stop here.
So thank you very much, Sonia. I have a few questions, but maybe someone else has questions as well. Milton.
Yeah. So I have some questions actually. Yeah, maybe we can go one on one.
Okay, fair enough.
I mean, maybe other people have questions too.
Yeah. So I have one question, which is the simplest one. So in your formula, actually, if I didn't misunderstood, the final answer, the quasi-potential does not depend on A and alpha and beta. It depends only on gamma.
Oh, sorry. Gamma is alpha plus beta over 2.
Yes, I know, but I mean, what I meant by that is that in principle, I mean, if gamma is the same for different alpha and betas, it doesn't depend on alpha and beta.
Yeah, right. Yeah.
So in particular, for example, if you take alpha equals beta equals gamma, the result is the same.
Yeah. I mean, there you're in the Bernoulli product setting.
Yeah. And so yeah, that's yeah.
I mean, the quasi-potential that you get in the end is the same as the one you would have for the Bernoulli setting, right?
Yes. So that was my next question actually. Yeah. Okay. Thank you.
Any other question? Okay, so maybe I can go. So the model you studied, you have a rate 1 boundary dynamics and a rate n square bulk dynamics. And the hydrostatic profile would be the same if you had a rate less than n boundary dynamics and a rate n square bulk dynamics. My question is it like doing the same thing that you did? Is it possible to encompass also this kind of any boundary rate that is less than n?
Yeah. So
what would be the difference? Would the quasi-potential be exactly the same? What would change is my question.
Yeah, so basically this picture adapts if you have usually you'd like to write n to the 2 minus theta and n to the 2 here.
Yeah.
And then so your question is what about theta, any theta greater than 1?
Yeah, exactly. But I guess if you change your n to the cube into something else, then you recover the right scaling, no?
Okay, so we basically did it for theta equals 2.
Yeah.
Right? Actually, it works for any theta greater than 1. And in the bulk, you have to look 1 plus theta.
Yeah. Okay. Yeah, that makes sense. Okay, and I had another question which now I forget. Yeah, so it's kind of a neat coincidence in some sense that when you look at the way to create a profile that is not constant, you have this equal footing competition between the mass change large deviation and the profile creating large deviation once you have the right mass. So if you take a look at models where the boundary dynamics is adjusted differently, would it always be the case that the mass changing large deviation would be on equal footing with the profile creating large deviation starting from the correct mass?
I don't know. This is a mystery to me. I mean, when you say unequal footing is
that the large deviations are both of rate of order n.
Yeah, right.
Because one of the two could cost much more than the other, theoretically, I mean. And I wonder, for example, you could imagine that, yeah, I don't know. If you slow down, yeah.
Okay, so basically what you're saying is
for example, let me take an example where if you accelerate very intensely your bulk dynamics, then the cost of creating a profile in the bulk might be very expensive, because now you average of a lot of jumps. but then maybe it would just change the time scaling of this phase.
Change the time, yeah.
Yeah. Okay. Yeah. Okay. That sounds reasonable.
I mean, the first thing we try to do actually is look at large deviations with speed n log n. But I mean, it didn't. We didn't get anything from it, and then we changed perspectives and thought maybe we have to change the observable. I mean, it's not clear to me. Again, this is at the heuristics level, so it's not clear to me why results should come from should work out because we took the right scaling. If it's just a coincidence, or if physically it means something, it's not clear to me, and probably that's why we can't make it rigorous for now.
Okay.
If you have any idea.
Yeah, well, at some point we can talk some more. It's very interesting, but I think it's a nice problem because it's the kind of problem where you can do like margin computation of what should be.
Yeah.
But it's not at all the same thing of doing the margin computation and actually proving the stuff, right?
Yeah.
So I was thinking, I have since try to see if this thing can be formalized. Let's look at the following very simple thing. So it's so you take a fixed graph, okay? So maybe big but fixed, and you select 2 or 3 points maybe of this graph that are reservoirs, and then you do exclusion on this graph. So now you want to now the parameter that is going to blow is the acceleration. So you accelerate very fast the exclusion, and you ask the same questions. What is the probability? Because if you accelerate the exclusion very fast, you get constant in time, and then you can show this type of large deviation things, no? And then you look at the and so now it's not it's not the empirical measure that has a meaningful large deviation principle, but it's the let's say the Bernoulli the Birkhoff averages.
The what?
The Birkhoff averages. So it's like you do. I mean, Donsker-Varadan, no?
1/t of integral of time occupation.
Yeah.
Okay.
So maybe, I mean, there is a similar type of question, so that the quasi-potential is going to be the sum of the quasi-potential of what you call the V gamma, because of course since you are accelerating the exclusion super fast, the density is constant on the graph, and then the density is the one that evolves towards the equilibrium density. And the Donsker-Varadan large deviations of the chain itself. I mean,
so you're talking about large deviations in large times, not in the scaling limits.
Exactly.
I don't know.
I mean, maybe this phenomenon of separation of quasi-potentials also holds there, and now you have a finite graph. Also, in principle, computations are easier, and maybe.
Okay. I hadn't thought of that.
No, I mean, maybe, I don't
know. Okay, I'll think about that.
Any other questions? Okay, so I think we can thank Sonia again for a very nice talk, and see you next week.
Thank you very much.
Enjoy your talk.
Enjoy your holiday, your bank holiday.
Okay, thank you.
Bye, everyone.
Bye.